So here's the second part of colligative properties. We did freezing point depression, boiling point elevation. Vapor pressure had its own video. Vapor pressure is sometimes included in the list of colligative properties, sometimes not. Colligative properties usually revolve around what the concentration of the solution is, not necessarily what's dissolved in it. So sometimes vapor pressure is included and sometimes it's not. Freezing point, in other words, freezing point depression, boiling point elevation, and osmotic pressure have concentration of solution calculations in the calculation of freezing point elevation, boiling point depression, and osmotic pressure. Vapor pressure does not. Vapor pressure has mole fraction of the solvent, pure solvent's vapor pressure. So, alright, so this one is osmosis and osmotic pressure. What osmosis basically is the movement of the solvent, the pure solvent, in a solution through a semi-permeable membrane. Now here's the trick. What you have to remember about osmosis, which is the pure solvent will move to dilute. So it's actually going to move from a low concentration to the higher. This is the solvent moving through the semi-permeable membrane, mind you. So the solvent moves to dilute. So moves from a lower concentration to a higher. So for example, in the picture you got your pure solvent on the left and you got your solution on the right. This is your semi-permeable membrane right here, and what's going to happen is the pure solvent moves to dilute. So it's actually going to flow into this side, and it's going to fill this side up to a certain point, and that certain point is going to be your osmotic pressure. Osmotic pressure is the minimum amount of pressure required to stop osmosis. Now, reverse osmosis is when you apply a pressure to push it the other way, and you're actually, if you look at the picture, you're applying an external pressure to push down so that you're putting the pure solvent through the membrane and not the solute, and you're going to get more solvent. This reverse osmosis method is used to get salt out of salt water and make it drinkable. And what they do is exactly what it says. They apply more than the minimum amount. They apply an external pressure to push it back down so that the pure solvent flows through the membrane and the salt gets stuck on this side, and this side here is going to be your pure solvent, which is going to be hopefully fresh water and drinkable. Another usage of osmosis is kidney dialysis. So osmosis is in the medical field and in any other industry for water drinkage. And there's a computation that goes along with this. Now notice this one also has concentration of the solution involved in the osmotic pressure. That's why this is part of colligative properties, to calculate the osmotic pressure. And again, notice it is dependent on the concentration of the solution. It's a pi symbol and it's pressure in atmospheres because the R is our good buddy R from the gas law chapter, so it's going to dictate the units for pressure and temperature. M is molarity, so unlike the other two, freezing point depression, boiling point elevation, which used molality, this is using molarity because this one is not calculating a change in temperature. The other two were, so this one can use molarity because it's not altering temperature. Alright, so you've got temperature has to be in kelvins because of R. This one uses molarity, unlike the other two, which was molality, because the other two are actually calculating a change in temperature. This one is not. This one is calculating pressure, so it can use molarity. Alright, a couple of definitions, and this is very big in the medical field. This is very big in biology. Isotonic versus hypertonic versus hypotonic are all very important terms in the medical community. Isotonic first. Isotonic means equal. Isotonic means equal concentrations. For example, a red blood cell, a normal, healthy red blood cell. You got the red blood cell, and around it you have plasma. In an isotonic situation, the red blood cell has the exact same concentration as the plasma surrounding it. Nothing transfers to or from the red blood cell, so you have a very normal red blood cell, and it's a beautiful picture of the red blood cell. All right, this is a slide of crenated red blood cells. What's happening here is that the red blood cells are losing fluid to the plasma. The red blood cells are losing fluid because the red blood cells are a semi-permeable membrane, and they are full of a certain concentration also. That means that if the red blood cells losing fluid to the plasma, then the red blood cells are in a hypertonic solution. Hyper meaning above. So I'm going to call it a hypertonic plasma. The solution surrounding the red blood cells is a higher concentration. So the red blood cells is losing solvent to dilute the higher concentration. So the red blood cells is losing, and they're becoming crenated, they're becoming shriveled up and dried up and losing their solvent to the plasma. And then the last one is finally a macrocytic red blood cell. And what's happening here, which is a hypotonic situation, the plasma is less concentrated than the red blood cells, and the plasma is the pouring into the red blood cells to dilute the more concentrated red blood cells. So the red blood cells are gaining liquid, gaining solvent, and what happens is somewhere along the line these babies are going to burst because they can only hold so much. So you have an isotonic where it's equal concentration. You have a hypertonic where one of the solutions is greater concentration than the other. And you have a hypotonic situation where one of the solutions is less concentrated than the other. And osmosis is when it moves to dilute. All right, so here's an example that I'm going to work. They give me the average osmotic pressure of blood at 7.7 atmospheres, and they want to know what the concentration of sodium chloride is. All right, first, sodium chloride is a salt. It's going to have a larger effect on osmotic pressure. There are 2 ions in sodium chloride, so it is going to have an effect on it. So we need concentration of sodium chloride. We're going to be looking for the molarity of sodium chloride that's going to be isotonic with blood. All right, osmotic pressure, molarity times R times T. Osmotic pressure is given. Alright, so here's how it goes. Osmotic pressure is the pi symbol being equal to molarity times our old gas law, R, times temperature in Kelvin because of R. Osmotic pressure is going to be in atmospheres because of R. They give me the osmotic pressure in the problem, and they are asking me for the concentration of the solution that red blood cells should be placed in order not to absorb or bust or become or lose or anything like that. They want an isotonic solution. So what I do is I figure out the molarity of the sodium chloride. Notice a couple of things. Thing number 1, the 2 is because there is no such thing as sodium chloride. There's sodium ions and chloride ions in solution. So if one ion has an effect on the osmotic pressure, 2 is going to have twice as much. So you just plug in the 2 and you do the math, and you get 0.157 moles of sodium chloride per liter of solution. This is going to be an isotonic. If you put the red blood cells into a larger concentration, the red blood cells will lose fluid to the sodium chloride solution, and the red blood cells will become crenated. If you put in less sodium chloride, if you have a less concentration than 0.157 mole per liter, then your red blood cells are going to be a higher concentration than the sodium chloride that they're in, and the sodium chloride solution will actually pour into the red blood cell, because in osmosis it moves to dilute. It actually moves from lower concentration to higher. Alright, colligative properties of electrolytes. Mrs. G, why do you keep throwing in a 2 for sodium chloride? Where is that coming from? Well, salts. Since the colligative properties, freezing point depression, boiling point elevation, and osmotic pressure depend on the number of particles dissolved, that's why sometimes vapor pressure is not included. Vapor pressure really isn't dependent on the particles. It's the mole fraction of the solvent and the vapor pressure of the pure solvent. That's why it's not usually included in the list. So really, colligative properties is just the 3. Boiling point elevation, freezing point depression, osmotic pressure. Now, since these 3 colligative properties depend on the number of particles dissolved, molality, molarity, solutions of electrolytes, strong electrolytes, which dissociate 100% when placed in solution, would show greater changes than those of non-electrolytes, which I've been discussing. So I've been taking into consideration the fact that I'm dealing with an ionic salt and how many ions come from that ionic salt. The Van Hoff factor is nothing really to calculate. You count. If you're dealing with an ionic solute and it's a 100% strong electrolyte, dissociates in water, you count how many ions it is, and that's the Van Hoff factor. And you plug that into your colligative property calculations, which I've already done. So here's a couple of examples I want you to write down. Alright, we've done sodium chloride. The Van Hoff factor for sodium chloride is 2, because there are 2 ions. Every one of these is a soluble salt. Sodium sulfate, how many ions is that? 3, because it's going to dissociate into 2 sodiums and 1 sulfate, so the Van Hoff factor is 3. Potassium phosphate, how many is that? Well, 3 potassiums and 1 phosphate, so 4. Aluminum sulfate, how many ions is that? 5. I've never seen one larger than 5, I'll be honest with you. These are all Van Hoff factors. So when you're doing boiling point elevation, freezing point depression, and osmotic pressure, if one of these is the solute, then you're going to throw this I into the computation. If it's sugar, if it's sucrose or glucose, the Van Hoff factor is 1. It's not an ionic salt. It's not going to dissociate 100%. Right, now, exceptions to the rule. Expected value for the Van Hoff factor can be just a bit higher than actual, especially in concentrated solutions. You have a cation and an anion in a concentrated solution. Somewhere along the line, they're going to be electrostatically attracted to each other and form a partnership, and is going to be counted as one entity. So you've got ion pairing going on. We always assume an ionic salt dissociates 100%, and that's fine, but in concentrated solutions, you've got them in such close proximity to each other, you're going to have an electrostatic attraction, you're going to have a pairing up, and that pair will be 1. Last thing I want you to know for this chapter. Alright, so the last thing I want you to know for this chapter, finding the molar mass from boiling point elevation or freezing point depression. Remember that the boiling point elevation is going to be change in temperature is equal to constant times molality. And most of the time this is going to be for large molecular compounds, so you don't have to worry about the Van Hoff factor, it's 1. Little manipulation. Molality is moles of solute per kilogram solvent, but moles of is grams divided by molar mass. So I do a little substituting in, do a little manipulation, a little algebraic manipulation, and I get change in temperature is K times grams of solute over molar mass times kilogram of solvent. A little more manipulation and you get molar mass will be equal to K, which is a constant, grams of the solute they'd probably give you in the problem, over the change in temperature times the kilogram of the solvent. Just a little algebraic manipulation. So what you basically are doing So on the left I manipulated the formula for boiling point elevation, freezing point depression. Since they're pretty much the same with the exception of K, I'm not doing it twice. So on the left I've done this manipulation of the formula, which I just described to you. On the right you can do it in a logical series of steps. You will find molality first of the solution. Find molality by delta T divided by K. That'll give you the molality of the solution. Please remember the definitions. Molality is moles of solute per kilogram of solvent. Probably going to give you the mass of the solvent in the problem somewhere. So it's just the molality times mass of the solvent will give you the moles of the solute. Molar mass is nothing more than mass divided by moles. Probably going to give you the mass in the problem. This is two different ways of tackling some of the more arduous freezing point depression, boiling point elevation questions. And that's the end of this part. This was part 2, I believe, of the, now this was definitely, yeah, I think I'm definitely cutting it into 2 parts. All right, so this was part 2 of colligative properties.